Now, let's do an example of a, well, stoichiometry problem given oxidation reduction conditions. All right, so we have example number 4. Will an aqueous solution of cobalt 2 sulfate of cobalt 2 sulfate oxidize zinc metal? That's the question. If so, find the mass of cobalt formed when 2.6 grams of zinc is dropped into a solution, dropped into, I'll tell you specifically, it's going to be 160 milliliters of a 0.95 molar cobalt sulfate, cobalt 2 sulfate, so it's going to be COSO4. So, will an aqueous solution of cobalt sulfate oxidize zinc metal? If so, find the mass of cobalt formed when 2.6 grams of zinc is dropped into 160 milliliters of a 0.95, let's make my 9 a little clearer here, molar cobalt sulfate. Okay, well, if I look on the activity series or the reduction potential, so cobalt is below zinc on the activity series. It's higher than zinc on the reduction potential, which means it has a higher reduction potential than zinc. So yes, cobalt will oxidize zinc. So let's go ahead and write it out. I have zinc metal, solid, plus cobalt sulfate. It'll turn into zinc sulfate. Zinc carries a positive 2 charge, so there's no balancing to do here. And we have, it'll form cobalt metal. Good, nice and easy. When we do the ionic, the sulfates cancel, and what we end up with is a net ionic of the following: zinc metal, solid, plus cobalt 2 plus, which is aqueous, turns into zinc ion plus cobalt metal. That's the reaction. This is what's happening. And again, the stoichiometry is 1-to-1, not a problem. So now let's go ahead and see what's going on. We have 2.6 grams of the zinc metal, so let's find out how many moles that is. So 2.6 grams of, oops, let me write a little shorthand. I'm going to specify zinc here so I don't have to keep writing it. So 2.6 grams times, well, 1 mole of zinc is 65.39 grams, giving me 0.0398 mole of zinc. Okay, now as far as the cobalt is concerned, I have cobalt sulfate. 1 mole of cobalt sulfate releases 1 mole of cobalt ion. So I have, let me put cobalt there, 0.160 liters, which is the 160 milliliters, times 0.95, that's the molarity, that's moles per liter, so that I can find the number of moles of cobalt and compare the two to see which one runs out first, equals 0.152 mole of cobalt ion. And again, it's moles of cobalt sulfate, but cobalt sulfate, as you can see from this, 1 cobalt sulfate releases 1 cobalt ion. That's what these ones, that's what these subscripts tell me. Okay, let's see. So now that we have 0.0398 moles of zinc, 0.152 moles of cobalt, well, let's do our limiting reactant. We can see just from here, because this is 1-to-1, 0.152 moles of cobalt requires 0.152 moles of zinc, but we only have 0.0398 moles of zinc. So it's the zinc that is limiting. And don't worry if we did that a little fast. We'll actually do it numerically next lesson when we do a series of examples in stoichiometry. So again, 1 to 1, I have 0.152 moles of cobalt. I need 0.152 moles of zinc. I only have 0.0398 moles of zinc. Not enough. Therefore, that's what's limiting. The zinc is limiting, so I have to use the 0.0398 in my further calculations. All right. Now, so we take 0.0398 moles of zinc metal, and the mole ratio of zinc to cobalt of zinc, this is ion, oh no, I'm sorry, this is zinc metal, moles of cobalt is 1 to 1, right? 1 mole of zinc produces 1 mole of cobalt, so that's 1 to 1. So I end up producing 0.0398 moles of cobalt metal and 0.0398 moles of cobalt times its molar mass, which is 58.93 grams per 1 mole, and I end up with 2.35 grams of cobalt produced. There. So there we go. We started off with some zinc. We started off with some cobalt sulfate. We dropped the zinc in there. Cobalt, because it's higher, has a higher reduction potential than zinc, or it's lower on the activity series. It will take electrons from zinc, turning it into zinc ion. In the process, the cobalt ion will turn into cobalt metal and fall to the bottom, hopefully fall to the bottom. It'll actually stick to the zinc. We can scrape it off later, not a problem. And theoretically, we can form 2.35 grams of cobalt. Okay, now I just want to give you some words of caution when dealing with activity series and reduction potential. Here's what happened. Let's use our example of zinc and magnesium. So zinc and magnesium. All right. If I take zinc metal, solid, and if I mix it with magnesium metal, there's going to be no reaction. And the reason there's no reaction is, well, zinc has the electrons it wants, magnesium has the electrons it wants, they're neutral. There's no real desire for electrons at this point. Metals generally tend to want to give up electrons instead of taking them. There's nothing going to happen here. There is no oxidation reduction. So when you see oxidation reduction potentials, it depends on what species you're mixing. In this previous example, we had cobalt ion. It's missing electrons. Therefore, since zinc metal has electrons, it will take them. But here, nothing is missing, so there's going to be no reaction. However, if I do zinc ion plus magnesium metal, now zinc is missing electrons, magnesium has electrons to give. Here, because zinc has a higher reduction potential, it's lower on the activity series, it will actually take the electrons that magnesium has to give. It becomes zinc metal plus magnesium ion. Well, another possibility is, how about if we do zinc metal plus magnesium ion? Well, again, zinc has a higher reduction potential than magnesium, but zinc already has its electrons. Magnesium doesn't even have electrons to give up anymore. Even if something were in the neighborhood that would pull it, there's no reaction here. And one more possibility. What if I had both ions floating in solution, zinc ion and magnesium ion? Well, yes, zinc wants electrons. It's missing 2 electrons. It is higher than that in reduction potential, but magnesium doesn't have any electrons to actually give up. Therefore, there's no reaction. So when you look at these oxidation reduction reactions, make sure that the thing that wants to be reduced is in ionic form, and the thing that's being oxidized actually has electrons to give up. So the charts that I gave you are specific in terms of the species that are involved. Zinc ion plus magnesium will produce an oxidation reduction reaction. No other combination will do that. So it isn't just zinc and magnesium metal. No, it's very, very specific about how this chemistry works. Okay, Thank you for joining us today at Educator.com for Oxidation Reduction Chemistry. We'll see you next time. Take care.